And we can move to the next talk, which is coming from Kristers Nagainis from the University of Latvia, Institute of Astronomy.
Yes, hello.
The title is a Program for Asteroid Detection on the digitized scans of Baldone Schmidt Telescope Archive.
Good afternoon. Thank you for having me. I'm a third-year bachelor student, and as the chair said, today I'm gonna talk about the program for asteroid detection on digitized scans of Baldone Schmidt Telescope Archive. And I will divide my talk in a few parts. So first I'm gonna tell you about the data which I'm working with. And after that, I'm going to explain how I made the automatization process of finding the asteroids. Then I'm going to discuss the results and conclusions. And after that, I'm going to tell you about my future plans. So the data I'm working with comes from Baldone Observatory. And you might have heard from the previous talk some kind of facts. So I'll just summarize. It is the 12th biggest in its category with 1.2 meter in diameter. And from 1967, from 2000 to 2005, made more than 25,000 sky scans. So that's a lot of data, and that is exactly what I need, because I'm gonna search for asteroids in other databases. But how do these scans look like? So on the left side, there's an actual picture of the scan. So there's a lot of objects, but this is not very useful for me as I will work with databases. So I use the table on the right, which is just all the variables containing the information about the objects in the left picture. So coordinates, magnitude, and stuff like that. So to search for asteroids in databases, I only need time and coordinates. But for further research, I need magnitude, intensity, and full width at half maximum to analyze the data. So yeah, with these parameters, I can try to search for asteroids in other databases. So how was it done previously? First off, yeah, I'll show a video how it was done manually. So first off, you choose which scan would you like to check out. So for example, I pick a 53rd slide scan, and I have to take the coordinates, the time, the date, and then I choose the database. In this case, I choose small body database from NASA, and I input all of the parameters, which is not a very fast process. I have to pick the observatory, put the center of the coordinates, also to put the width and length. So the region is defined, and also some constraints. Then I have to wait for the asteroids, and when they output all the asteroids, I pick one of them, pick their coordinates, and then I go to my Baldone Observatory data, and I have to find a match between these coordinates. But it is not as easy because there's, of course, some errors, some uncertainty, and that's why you can't just put Control F and find it. You have to basically scroll through and check if the coordinates lie in the uncertainty region. So it's a tidy work. And to go through one scan, I had to spend almost 40 minutes to check all of the asteroids, which is a long time. So a program would be a lot better. To make a program, to make an automatization of this process, I need a plan. So from the manual search, I can understand that first I need to find the information to put in the NASA database. I have to make the program which can input the information, which can then search for these output asteroids in the Baldone data. And then I have to save them and save them in some kind of table, which is readable also for other users, not only for computer. So I'll show you now a video how the first two steps were done. So no human interaction is needed anymore. It just picks a scan and inputs all of the parameters way more quickly. And yeah, then it outputs all of the asteroids, which is nice, which is way faster. And the process of searching is also very simple. So you pick the asteroid, the program just iterates through all of the objects, and if it finds a match, it saves it in table. If not, it just goes to the next asteroid. And yeah, the table format is this is not very readable, so I used the most common one to input the both parameters from the Baldone Observatory data and from NASA database. So yeah, this is more readable. And if we compare time, which was spent, approximately 150 hours would have to be spent to do this manually, which is a long time. And it's of course not for 25,000 scans, it's just a small portion. I think there were 300 scans in this particular case, and only 5 hours were spent for the automated version. So it's 30 times faster, which is exactly what I need. But for the asteroids which were found, I found 131 asteroids in U-passband scans. And to see if my program works or not, I compared it with the previous study where these asteroids were searched manually. And 88 asteroids matched with the previous study from these 131, and 43 were new asteroids. So this is a good result, because it means that with this program I can find new asteroids which couldn't be found when it was done manually. And yeah, now I'll turn to the results section. As I have a lot of data, I can plot them and try to seek some relationships between the data. So for example, here I plot in a red or orange the asteroids compared to all of the objects. On the x-axis I have intensity, and here I have full width. And from now I can see that there is not a clear distinguishable relationship. Also where I choose different axis, for example, magnitude and ratio, and ratios, and I chose intensity divided by full width. So here I can see some kind of relationships. This might be exponential. And so my hope is, if everything goes as planned, I can find some kind of function that, for example, I will be able to find asteroids which are not yet discovered, which are not in other databases yet. So if the exponent goes like this, maybe I can find an asteroid here. So this was my initial goal. Before that, I tried to analyze data. So this is a density plot. I can see the most asteroids like here. I can also analyze it with the histograms and compare it with other data. But it is important to compare it with all of the objects. So here I make the exponential fit. And I can see that all of the other objects are all in the same region. So I can't really tell if this relationship is for any use or not. So I use density plot for all of the data in purple here. And I can see that the most asteroids lay in the same region where is the biggest density of all of the objects, which is not good because this exponential fitted curve is very similar to the density plot of all of the objects. And from that, I can tell that I will not be able to tell 100% that if the asteroid is on this line, that this will be an asteroid. It might be a star or something. So I tried to make a probability determination. So I picked the region in the red, which is the confidence band here in green. And I just divided all of the objects which are in the region by the all of the asteroids which are in the region by all of the objects. And the results were not also very good because the probability was in order 10 to the minus 6, or in a different region from 9 to 10 magnitude, 100 times better, but it's still small. So I did the same thing with a different relationship intensity to full width. Here I fitted logarithmically. It's the same situation. The density is similar to the fitted line, and the probability is also pretty weak. So my last hope was to make a clustering model, but it also, you can see on the lower left that I had 4 groups, and the asteroids were covering all of the groups. So I can't find specific groups for asteroids with clustering model technique. So this didn't work. So I tried to explore other interesting regions. For example, in this magnitude ratio graph, there's a very interesting region with high ratio objects. So I made a clustering model for them. And it's interesting that where there are 4 groups, I put all the objects in a SIMBA database and checked, so what are these objects? And I found out that the blue objects are nothing interesting, just basic stars. But the yellow group was binaries, supergiants, and proper motion stars. The violet group was mostly pulsars and B stars. And the green group was BE stars, supergiants, and pulsating stars. So it means that with this clustering model, I could distinguish between different categories of objects. I also tried to do it within density around 200, but the clustering model didn't work so well because it chose a lot of groups and I couldn't do the same experiment. So I need further research for that. The good thing is that from these 3 groups, at least I could distinguish between them, which is which, even if I couldn't do it when I tried to distinguish asteroids from all of the objects. So, in conclusion, automated asteroid searching is significantly faster and more flexible because I can choose a different uncertainty region, and I can also use it for different data sets. I found more asteroids than in the previous study. Well, maybe not more, but some new ones at least. And talking about differences, there is no obvious difference between asteroids and all of the objects, but I could categorize specific object groups. And further goals is to further research some specific groups, which could be categorized, and also to do the same experiment with the different bands, for example, V band or R band, and maybe even to try to find asteroids from data which is not yet processed. So thank you for your attention, and do you have any questions?
Thank you very much for your talk.